In this video, we're going to talk about the division algorithm. So this is our continuation of number theory here. So division algorithm says, basically with the division, it's not an algorithm, it's a theorem. I mean, there's kind of an algorithm involved, but basically what the division algorithm says is that if you were to take some number, say 100, and divide by a positive number, say 9, then what you get is a quotient and a remainder. So you would get 11 with remainder 1 because 100 is 9 times 11 plus 1. And moreover, these numbers are unique if you expect this to be the remainder, meaning that this number is somewhere between, if we're dividing by 9, then the remainder has to be between 0 and 8. So for example, if I could also write 100 as 9 times 10 plus 10, but now the problem is that that's no longer the remainder because you can get another 9 out of that. So that remainder is not unique. But barring that silliness, the division algorithm is a proposition which says that these numbers are unique and moreover they have names. So let's get into it. So for all integers a, and for all positive integers, let's call it d. So for all positive integers d, there exist unique integers. So there exist unique integers. We'll call them q and r. Q and r, such that a is equal to dq plus r, and r is between 0 and d minus 1. So these are all integers, like everything else that we're doing in this chapter. Everything is an integer. And this is a proposition, so that means that we can prove it. And there's going to be two proofs. One proof is going to involve what's called the well-ordering axiom. And I think that this is important enough that we should go through this. I'm actually going to give you two proofs, and the purists among you might say, why two proofs? One proof is good enough, and it is, but both of these ideas are going to be relevant for us, and they generalize a little bit differently in different situations. So I think it's important to go through both proofs. So the well-ordering axiom, this actually is not a part of the proof. Let me just remind you what the well-ordering axiom is. This is something that, I'm not sure if we got into this in the induction section or not, but this is an axiom, like it says in the name. And remember, axioms are statements that we assume are true. So this is something that we can't prove itself. It's an axiom. We're assuming that this is true. But what it says is that every non-empty subset of let's say the natural numbers, remember with the natural numbers, you can include 0 or not. Let's include 0. But every non-empty subset of the non-negative integers has a smallest element. Okay, that's not a controversial fact, but it is something that we need to assume is true, and it's not true of every set. So for example, if you replace the natural numbers with the integers, there is no smallest integer. By smallest, we mean closest to negative infinity. So large in the negative direction, like as far over on the number line as you can imagine. But there is no smallest integer. There is a smallest non-negative number, and that's true of every non-empty subset of the non-negative numbers as well. Okay, and so this is the fact that we're going to use for the first proof of the division algorithm. So for our proof, what we're going to do is, given the integers a and d, so let me be a little bit more precise. They're not just integers. A is arbitrary, but d is a positive integer. What we're going to do is we're going to define the set, and I'm going to call it S, and it's going to depend on A and D. So it's going to be S of A, D. It looks sad. And it's going to be the set of integers of the form a minus dx, such that x is an integer and a minus dx is greater than or equal to 0. So just to kind of get an idea of what this is going to look like, again, not part of the proof, but let's just off to the side say that we have 100 for a, and our d is 9, like we did before. And then we're going to look at s 100 comma 9. It's going to be the set of integers 100 minus 9x, such that x is an integer and 100 minus 9x is greater than or equal to 0. And so this is going to include the set let's see, if x is 0, we get 100. If x is 1, we get 91. If x is 2, we're going to get 82, and so on. And so there's going to be a sequence of numbers here. This is going to be 1, 10, and then it's going to go up and up. And it won't have a largest element, it just has a smallest element. So in this case, the smallest element is 1. Okay, but that's what the set is. So it's the set of integers of the form 100 minus 9x, where x is an integer, and where 100 minus 9x is greater than or equal to 0. Except instead of using these numbers, we're doing this in general for values a and d. So that's what the set is. And if you notice, it's a subset of the non-negative integers. So since S sub AD is a subset of the non-negative integers, then the set has a smallest element. That smallest element let's say a minus d q, right? There's some integer q where that's going to be the smallest element. Okay, so we'll call this r. So we'll call this value r. Okay, so r is equal to a minus dq. Now, what we need are two things. We need not only that these numbers exist, okay, and so existence we get from the well-ordering axiom. There's really not too much to say there, but we also need to prove uniqueness. So how do we prove uniqueness? So we know that there's this unique value a minus dq. We're calling it r. But what if the value is not unique? So we need to think about that. So I want you to think about how do we prove uniqueness, and then I'll come back in the next video and we'll do that.